Okay, so we'll talk about ARM design philosophy. So there's not much about ARM design philosophy to talk here. So I'll just tell you everything in what to say in a small short version. So in the textbook you have like just 2 pages about like this half page and this like half page. So you can see there like this bullet points, right? So here you have multiple paragraph, each specifically speaks about one feature or the one thing. So that has been like filtered and wrote in points over here. So there are 6 points over here which you have to know about what to say ARM design philosophy. So the key points for better marks in video, so you have to remember this. See, if you mention these points, that's more than enough. I mean, like if you mention, you'll be able to write one or two things, but I also have the explanation over here. So low power consumptions. So it doesn't use much power for the device. Like it's simply like essential for battery powered devices like mobile phones and PDAs. So it basically means that it reduces the power consumption so that it is easy and good, like essential to use in many devices. And it is also a like a good feature for a device. Like it's simpler, like it doesn't use much power and makes it like go heat or something like that. So low power consumption, simple meaning that essential for like phones, like it optimizes the battery consumption and doesn't make the device use more power, like that you have to say. High code density in the sense nothing but the codes are like short but very deep type. Like instead of writing one 10 to 20 lines of code just to print hello world, you can simply like how Python is like just in one line you can do that. No, it's just like that. So it saves memory space, making ARM ideal for cost sensitive application. So usually memory, takes a lot of cost and all, like memory storage device and all processing stuff. Then cost efficiency, it supports low cost memory devices, reducing manufacture cost. Small die in the sense they are space available for specialized peripherals on the embedded system. Like it doesn't occupy the whole area. If you want further enhancement or in like you have seen that board, right? Like for embedded system, if you want to use additional features or additional instructions or stuff, you can just add or solder, like you can simply connect those things in the circuit board and motherboard like that. Then hardware debugging. Okay, so allows software engineers to debug efficiently, reducing development time. So in the sense, hardware debugging is not that difficult, nor it creates much errors or something. So the manufacturing, I mean the development time is reduced so that you can easily develop and introduce into the market. Balance risk approach, like ARM is not purely risk but optimized for embedded system performance. Instruction set for embedded systems, as you can see, that's what oh, not this textbook. So that's what they had given in this. You just had one extra subsection 1.2.1. See, variable cycle execution, inline barrel shift, barrel, sorry, thumb 16-bit conditional, same thing. It's over here, which I'll just explain you. Variable cycle execution, nothing but few instructions are executed in only one cycle, but some instructions take multiple cycles for better efficiency. That's all you have to know about variable cycle execution. You can simply elaborate it in your own words, or if you just want to pass, you can write only this much and finish it. Inline barrel shifter, a hardware unit that modifies register values before use, enhancing performance. So you just have to know that before the register is being used, so this hardware unit modifies the register value. It's good for performance and stuff. If you want to check in this thing, you can also check over here. So before the input registers, they have used the word as input register. You can use the same word as well in the exam. If you want to use, it's up to you, but make sure you just refer to textbook once. It's like once you read this and then go to textbook, you will have a bigger picture in your mind, and you will be able to answer it very effectively. Thumb 16-bit instruction set, it has both 16 and 32-bit instructions, and it improves the code density by approximately 30 percentage. It see, whenever you talk about code density, you just have to remember that instead of writing hundreds of lines of code, you can just finish it in like few lines. Like it's called density of the code. code density can be, high code density in the sense long length of codes, low like that. So just understand code density means reducing the length of the code. So it helps to reduce the memory usage while keeping execution efficient. Okay. Then next we have conditional execution. As the name said, it will execute only under certain conditions, else it will not execute. And why does it do, and what is the benefit? Why does it do? It has its own purpose. Why does it do is because of what happens because of it. So it reduces the unnecessary branch instruction. So you understood like why it is used is just to reduce the unnecessary branch instructions, and it helps in that particular thing, so that it improves the performance or something like that. Enhanced DSP. So DSP is a digital signal processor. Like let me just confirm. See, signal processor instructions are added to the standard ARM instruction set to support fast. So this is much better. It supports fast 16x16, like 16 into 16 bit multiplication and saturation arithmetic for better signal processing. See, digital, it's over here like better signal processing. So you can see here focus on how ARM improves embedded system performance. It uses example like mobile phones, PDAs to strengthen answers. You have to mention about examples and all those points. Draw simple diagrams for load, store, or thumb set. Actually, there is no diagram given over here, but you can always get it from the Google or something. And then the next topic is 1.3 ARM system hardware. So we can successfully put a tick over here that we have completed this topic, and now we'll move to, okay, so this is embedded system hardware before. Okay, oh, that's correct. Like we'll just move to the next question. Okay, see you in the next video.